Hello, I'm Umnik. I will solve educational to the first round and try to explain what I'm doing. In problem A, have n monsters. For each monster we know its health, and we can cast spells. Each spell can either kill one monster or choose two monsters and decrease their health by one. We need to find the minimum number of skills to kill all of them. Okay, if we use second skill on some monster, then it doesn't make sense to use any other skills on him, so we can just remove them and well, it kind of doesn't make sense to use first one on monsters that have at least 2 health. Like, this spell deals at most 2 damage, and this spell deals like HP of monster damage. So we have to do like sum of all the HP damage. So if we use the first spell only on monsters that like okay, obviously we can kill everyone using n spells of the second kind. Suppose we can use less spells. So suppose it's n minus k, so it's less than n by 1. The second spell can only kill one monster, so we have to use the first one at least 2k times, because like at least k times, like at least k times we should kill at least 2 monsters with one spell. So we have to use this one at least k times, but that means that total damage we will do is bounded by like sum of n minus k, n minus 2k biggest HP, which we will do using this, and k times 2. So that should prove, after careful consideration, the obvious conclusion that we already know, that like we should use the first spell only to kill 2 monsters of health 1. So the answer is like n minus number of ones divided by 2 rounded down. Like how many times we can kill 2 monsters using the first spell. That will be the number of spells we will save. So we only need to calculate the number of ones. and then print n minus number of ones divided by 2 rounded down. In problem B, we have like 4 sets of jokes. For each set, we're given the number of jokes in that set, and each joke is kind of like each type is just a mask of 2 people, whether they like this joke or they don't. We want to order the jokes so that when we read the jokes in order, if somebody likes the joke, he gets +1 to the mood. If they don't like it, they get -1, and we want their numbers to be non-negative for as long as possible. Well, it should be clear that we should always start by telling jokes that both people like. Like, why not? If we have some order and there is a joke that both like, that is not like in the beginning, before every other joke, we can move it to front and it will not be worse. Then we shouldn't tell jokes that nobody likes unless we don't have any other material. And then we can just calculate how many jokes of other types we can say. This problem seems easier than the first one. So we start by telling all A1 jokes that both like. Then we will tell at most A1 jokes that when we tell a joke that one likes and the other doesn't, we do like +1 in one of them and -1 in the other. So if we will switch them, it will be fine. Like we after telling 2 jokes, we will return to the same state. So actually we need to just check that we have at least one joke of this type. So if there are no jokes that both like, we can only tell one joke and one will get negative value right away. Otherwise, we will switch between B and C after telling all of the A jokes. So the answer should be A plus 2 times mean of B and C. That's how many times we can switch. And then we have absolute value of B minus C jokes left, which will disappoint one of them, and also the jokes that will disappoint both of them. But if we focus on the one we will disappoint with this kind of jokes, like he can only stand at most A of them, and on the next one he will leave, so we'll add minimum of A plus 1 and the number of jokes we have, which is absolute value of B minus C plus D. Okay, in problem C we have a permutation. We want to sort it by performing the following operation. We choose two different elements, take them out, and insert smaller of them in the beginning and the larger of them in the end. Right. And we want to calculate the minimum number of operations to sort. Well, as usual in this kind of problems, we want to kind of delay making our decisions and look at the numbers that we don't touch. So we can imagine that we are doing we can choose on what numbers, in what order we will do the operations, and then take them out and then insert. So if we do k operations, then we will not touch elements at least n minus 2k elements, but in the end, after the sorting, if we do k operations, we will k times insert something in the beginning and k times insert something in the end. So n minus 2k middle elements, not the first k and not the last k, we didn't touch them, so the relative order is the same. So we know that in the end we want to get a sorted permutation, so it's identity permutation. So if we can do it in at most k operations, then we know that this middle segment of length n minus 2k in the identity permutation should be in correct relative order, because we cannot touch these elements. And if it's true, it should be possible, right? We start by we know that there is a correct segment except prefix and suffix of length k, and we can increase it by 1, take the numbers that we want to insert in the correct order, take them, make the operation with them. Now everything in the middle was a subsequence, and we appended the leftmost element and the rightmost element on the right. So in one operation we have decreased this k by 1. So we just want to find the smallest value of k, so that this middle segment in the correct order. It's obviously can be done with binary search on answer on k, but we can do it in linear time. We can start by having 0 or 1 elements and then move them in sorry, somebody calls me. I love spam calls. What I was doing here? Right, we were solving a problem. So we can start by start with very short segment, and then try to increase it, move both borders. And we need to check that by inserting these two elements, they're still in the correct order. But if we for each element we will find its position, so kind of construct an how do you call it? Inverse permutation, something like that. Yeah, we will be able to check that our new leftmost element is before the old leftmost element, and new rightmost element is after the old rightmost element, and we can increase the segment one step at a time. So that solution works in linear time. You need to be careful with initialization. It will be different for different parity of n. If n is odd, we'll start with one element, and it's always in the right order. But if n is even, we can either start with 0 elements or 2 elements, but in both cases we will need to handle the first 2 elements specially. Either we will have to check that these 2 in the correct order and start with them, or when we start with 0, when we add first 2 elements, we don't have anything to compare with. So, well, we don't have anything to compare with, but if we just like compare leftmost with the next number and rightmost with the previous number, it should be fine. So yeah, we can just write it accurately, then we don't need any special cases. So I only need the inverse permutation, so I won't store the original permutation. I will just store the inverse one right away, make it 0 index. Okay, now we will start with this k, which is which corresponds to segment of length 1 if n is odd. Like, remember that the length of our segment is n minus 2k, so if we initialize k like that, it will be like n modulo 2, so it's 1 if n is odd and 0 if n is even. And now, while k is greater than 0, we want to check that we want to decrease it by 1. And what would that entail? So when we are increasing k by 1, our new leftmost element will be decreasing k by 1. Our current leftmost element is k, our new will be k minus 1. So we want to make sure that it is to the left of k. And our new rightmost element will be n minus k. And it should be to the right of the element that is 1 less than it. In problem D, we have n permutations of length m. App is very small, but n is kind of big. And find a beauty of a permutation as the largest k, such that the first k elements are the smallest k elements in order. So it's like largest common prefix with a sorted permutation. Okay, then we define the product of two permutations as, well, their composition. Right. And for each I, we want to find the largest beauty of a permutation AI times aj for each I. So we are not interested in just one value, we want to find n values, like for each permutation. what is the biggest possible beauty when we're taking composition with this permutation. But yeah, composition is not symmetric. Well, how do you call it? Commutative. So we want to check, like, for each I we need to find j, and I is the first one. So we first apply AI and then apply the other one. Okay, let's see. So how to check if we can have beauty, B-A-U-T, at least K. What does it mean? It means that for each I most K, Ri is equal to I, and that's it. Like, maybe the actual beauty is larger than that, but if we are interested in having beauty at least something, we will only look at the first K elements. So Ri is Q P of I. So for elements from 1 to K, this should hold. But we can apply the inverse permutation of Q. So the inverse permutation of Q element I should be equal to the Pi. So if for like we want to find the largest K for which there is an inverse permutation that has a common prefix of length K with our given permutation. Well, let's just take all our permutations for each of them, compute the inverse one, and put it in try. Like now it's a problem on strings. We have some set of strings and we have queries. Query is find the largest common prefix with some string from the given set, and that problem is solved by try. Kind of a weird problem. Like, do exactly what is written in the statement. And why m is so small? Just for m to be b? Like, the input is of size n times m. But like, why not give a limit on the size of input? A bit weird. Or like maybe it's to not use map, like since the size of our alphabet, like our strings are permutations of numbers from 1 to m, so we have m different letters, so we will have n times m vertices in try, and for each we have to store the transitions, but like there are only 10 possible transitions, so we can just store an array instead of map, and that like n times m squared memory, which would be a lot if m was bigger. We can do it in n times m memory, but with log m overhead from map, and maps are generally slow. So probably that is the reason. Okay, so k will be the number of vertices in tree currently. Try. So we need to clear it between test cases. We need to create root in the beginning. So in the beginning, the try is just root and nothing else. After that, we'll iterate over the permutations, read the permutation. Now we actually have to store it, make it zero indexed, and construct an inverse permutation like this. So now B is our inverse permutation, and we need to add it to try. So we first stay in root, and then try to go down the try, and if there is no vertex using the edge we should use, we will create it. So if there is no corresponding edge, we create. Okay, so now we have the try, and we will just again iterate over everything and just calculate the answer. Calculate the answer, we will once again try to feed this string into the try, but now we do not create new states, we just stop if there is no new state. So while case most m, we are trying to go. If we arrived at non-existent vertex, we stop, otherwise k plus pause. And the k is the answer. I used it's okay. Yeah, it's like redeclaration, but like, I mean, how do we call it, like shadowed variable, but it should be fine. I don't actually need to know the size of the try after I have constructed it, so it should be okay. Okay, what will happen if I swap the permutation and its inverse? The answers become incorrect. Okay, so that's not what's happening. Let's fix this. Just in case, but that shouldn't be bug. don't think so. I read this statement. This is correct. That shouldn't have. It doesn't. I really don't get it. Okay, let's. Let's write stress test, I guess. So for stress test, I want the stupidest implementation of what is written in the statement. So I want to apply AI first to k plus 1, then apply AJ, and if it is k plus 1, we should do k plus plus, and then update the answer. Should be called the good. What is that? That's not the correct way to use print. Okay, this is weird. I don't understand something in the statement, I guess. Or maybe I'm not cleaning something. clean something, right? Like, oh, but how is it possible? So yeah, it's about multitest. Ah, so I can decrease k, but clean only like up to m in that test, and then reuse that, but it's not cleaned. Amazing, amazing. Um, okay, that was interesting. Um, okay, back on track, I hope. Um, what a weird statement. Okay, so we have a multiplication table, which is just like aij is I times j. We are given a number, which is a product of two numbers, and those numbers are up to 10 to the 9th. Then we need to do something for each divisor, so I guess like this form is given because they don't want to ask for fast factorization. Like we can factorize this number and this number, then merge their factorizations, get factorization of m. So now we have a factorization of m. We can iterate over all the divisors in some brute force form. So we have a divisor, and in the form of its factorization, we need to check, does this number occur in the multiplication table, and if it does, what is the minimum row that contains that? What does it mean? Like if it is contained in the is row, then it means that d is divisible by I, and d divided by I is at most n, because we can only multiply by numbers from 1 to n. Okay, so like instead we can find the largest divisor of d, which is at most n, and then d divided by that divisor is the answer, if it is at most n, because like the smaller the I, the larger the d divided by I. Okay, so we are given a number in some form, and we want for each of its divisors find its divisor that is the largest, given that it is at most n. That sounds simple, like that's just some simple DP. Like if this number is at most n, then it is its largest divisor that is at most n, and if it is not, then we can try to remove one prime number from it and take max of answers for those things. If implemented exactly like that, like we can just write down all the divisors. There will be something like 200,000 of them, like the numbers up to 10 to the 18th, I think have at most 200,000 divisors. So like for each of our 10 tests, we can find 200,000 users, sort them, for example, and then try all the prime divisors, but then we need to like take the DP value. For that we need to find where is it stored, and like if we are using map or if we're using some lower bounds, it will be additional log of overhead. It is probably fine, but I guess we can do without that, because we can do like all the transitions for the first prime divisor, then all the transitions for the second prime divisor, and it will be fine. Like for each, if we want to reach like from one divisor x to the other divisor y that is divisible by x, and we want to make sure that like if x is the answer, there should be a way to reach it through our DP transitions in order. We can like multiply by the remaining prime numbers in increasing order, non-decreasing order. That's the order in which we will do the transitions, so it's fine. And why is it better? Because instead of binary search, we can do 2 pointers. Like we will maintain will run through all our divisors of m and maintain a pointer on the value that is the current divisor divided by the current prime number. So that's linear for each prime. So that works in number of divisors multiplied by log. We need to sort. We have at most log different prime numbers. That's number of divisors times log. That should be fine. So I want to find all the divisors. First I need to calculate the factorization. I will write it here at some point, but I can use just map at first to store the power for each prime divisor. So I'm just factorizing the two numbers that are given, but storing their prime powers in their common map, because I actually need the factorization for their product. So now I want to write this factorization down in a way in which I will be able to then accurately write brute force that will generate all the divisors. So like in the array. Now writing brute force, you need current position and current number. So in brute force, if we have traversed all the prime numbers, x is the number we get. So we just store it here, and that's it. Otherwise, we need to try all the possibilities for the prime of for the power of the current prime, and it should be at most p pos 1. So I want to multiply x by p pos 0 in the power I, and I can do it like inside this cycle. So I first call make the next recursive call and then multiply x by my prime number. So now in array A of size m, I have all the divisors, but they're in some order, so I will sort them. Now I will have to initialize the DP. If this number is at most n, then its DP is just equal to that number. Otherwise, I will say that it's 1 for now. I remind you, I want to find the largest its divisor that is at most n. Now I will iterate over the prime divisors of my number, and now I will do 2 pointers. If my number, this divisor is not divisible by q, then I cannot divide it. So if it is non-zero, I will just don't do anything. So if it is 0, then I have to do something. I want to find number x, which is aj divided by q, and I do it by moving this pointer until I find it. I know that all the divisors of all the divisors are among the divisors of n, so it should be there. And now I can do update in dp. And now the answer for each one is just like the number divided by dp if it is smaller than n, well, at most n, otherwise it is 0, says the statement, and we want to find their XOR. Sure. Why there are 2 numbers? Number of divisors that are present. Okay. If we have a complete graph, we have to paint the edges into red and blue. So we're choosing red graph and its complement will be blue graph. Set of vertices is red connected, if it is red connected. Yeah. We have to paint the graph that there is at least one red edge, at least one blue edge, and for each set of vertices of size at least 2, S is either red connected or blue connected, but not both. And we want to calculate the number of ways to paint the graph. And n is up to 5,000 in easy version and 50,000 in the hard version. The tail is pretty big in both. Okay. The module is constant. So, theoretically, we could recalculate all answers locally and just print them. Well, at least in the easy version should be possible, right? 5,000 numbers is not that much. Like 5,000 times we need like 9 symbols, and we can compress them. But I think for 5,000 we shouldn't even compress anything. It will be like 60 kilobytes. Surely it is possible to submit 60 kilobytes on Converse. So we will be fine for easy version with cubic algorithm probably. But we don't have anything right now. So some set of vertices can be bad both when it is not connected in both cases and when it is connected in both cases. Can it happen at all that it is not connected in both cases? I don't think so. Like, let's look at red components. There should be at least 2 if it is not connected by red, but then we have all edges between components, and like if I want to reach between 2 vertices from different components using blue edges, there is just a direct edge. Otherwise I will take a vertex from a different component, and like if I want to go from here to here, I will go here and then here. So by one color it is surely reachable. How do we make sure that it is not reachable by both? Like for sets of size 2 and 3, we are fine independent of what we do. There is just not enough edges to draw 2 trees on 2 or 3 vertices. But for in case of 4 vertices, it should be possible to draw 2 trees, right? Yeah. So this combination is bad. We know that the whole graph is connected by one of the colors. Let's say it's connected by blue colors, for example. So it shouldn't be connected by red colors. So there are red components and all the edges like this, like this, like this do exist. So if we find red components, if we choose red components, all the edges between them should be blue. This set is red connected, so it shouldn't be blue connected, and like on this graph it should be a valid solution. And if we take so if we look at some set of vertices, if it is not inside a red component, then it is not red connected. Obviously, it was not connected in the whole graph, it is not connected after deleting some edges. And we know that it is blue connected, just because it is impossible to construct a set that is not connected with both colors. So we need to split our graph into components, then take solutions for them, and then just add blue edges here. So there should be like some very simple quadratic DP, like answer for size n. Let's say that we fix what color is the topmost one, then we just multiply the answer by 2. We can always flip colors. So the number of ways to make it like not red connected is like we split it into non-empty components. So like take the sum over we will split into several components. Some of their sizes should be n, k is at least 2, all the components at least 1. Or is it at least 2? If no, okay, well, 1 is fine. Right? And then we need to calculate the number of ways to split our graph in that number of components. That is done by this multinomial coefficient, but also wait, no, this is not correct. We can first like choose the component that contains vertex number 1. There will be like n minus 1 divided by m1 minus 1 factorial times n minus m1 factorial ways to do that. Then we take the next vertex, like the smallest vertex that is not chosen yet, and choose the component for it, and like this array, the sizes are in order. One, and so on. But actually when we like this and this almost equal, we only have one more number here. So yeah, it should be something like that. But this is actually not very helpful because that's a lot of variables. But we can just say that we will choose a red component that contains 1. Oh yeah, and then we like multiply by all the ADPs, because inside we need to construct a valid coloring that is not blue connected now, but that's the same thing. So that's just multiplied by product of ADP. What we can do instead is we can say that an is so we try all the sizes of the components that contain vertex 1. So if we fix the size, then there is this number of ways to continue. Then we have to multiply by AS, and then for the number of ways to like continue that for the graph of size n minus s, and it will be either one component, one red component, or it will be several red components. So instead of doing this, let's say that we will calculate b, like the number of ways to choose several more than one red components with total size n, and then like we choose this number is the answer for we have to choose a component for vertex number 1. We choose the size, choose the vertices, then color this component, and after that we can either just take one more, or we can take several red components. So we have this. And we can recalculate both these values, like an it's just bn. That can be right. Well, I guess it can. That kind of makes sense. We are choosing a red component for vertex number 1, and everything else is either red connected, that's this case, or it is blue connected. Then it is several red components, which is this, but like the number of blue connected graphs is also just a n. Yeah, okay, so what we are saying that a n is just 2 times this. Okay. Well, this is obviously calculatable and square time, and the limitations are not that big. Is it really true that we cannot just write n square and get accepted in the hardware? But I guess there should be something with FFT, right? Like, we should be able to divide something by factorials, like rearrange this thing. There is online of that kind. So if we say that n is an divided by n factorial, then fn is equal to 2 divided by n sum of from 1 to n minus 1 f s times fn minus s times s, right? Multiplied by s divided by s, then this becomes s factorial, and as divided by s factorial is fs, so it's s times fs times a n minus s divided by n minus s factorial, which is f and s, n minus s. So, yeah. And we can, like, I don't know, we can call this gs, so gn is n times fn, then gn is 2 times gs times fn minus s, And now we can do some kind of divide and conquer. Suppose we have calculated everything here, so we know both f and g. Now we want to calculate it here. We will calculate all the summands that in which both this thing come from this part, and then when we will solve this, we will recursively we already know all the summands that we can calculate, and so then we recursively solve this half. After we do it, we will calculate how this half contributes to this half. Yeah, that's how a line of two works. So we have 26 minutes. Let's just write n square first, submit it, get accepted, and go home. Yeah, let's just calculate it in this way, right way. Why not? So it will be f. I'm using f factorials. So factorials will be ff. So then f and g of 1 is 1. F is a divided by n factorial, and g is f times n. So we said that g of I is convolution of f and g, and then multiplied by 2. And f is g divided by f. Let's just divide, whatever. Then the answer is f multiplied by n factor. Wrong. I guess b is equal to a for all n greater than 1. So this one comes from B. It is transferred to F here. So when S is equal to n minus 1, we don't have to multiply it by 2. I mean, we have to not multiply by 2. So it's no. Still incorrect. Okay, let's try to write it correctly. So an should be 2 times from 1 to n minus 2. This is a n minus s, and also a n minus 1. If the red component of the first vertex is of size n minus 1, then the last vertex is just connected to everything in it with blue color, and yeah, that's just one option. Okay. So if we divide it by n minus 1 factorial, we will get gn is equal to 2 times alright, this is plus divided by n minus 1 factorial, it's f and so. So, mm, mm. But that's bad. What's here? I don't know. And actually, like, I have to subtract 1 for the color, everything in that color, and then multiply by 2 because I can switch colors. So the answers are actually bigger than they have to be. Still not right. should be 4 here, right? The number of graphs on 3 vertices that are blue connected but not red connected is 4. We can either have 0 red edges or every one edge can be red. And this is correct. So what's wrong? When I is 3, we will have here g of 1 multiplied by f of 2, which is 1/2. And that means that we have chosen component of size 1 . There should be 2 options, but G is here, and when we make red component of size 2, that happens here. Oh yeah, I wrote this incorrectly again. So here I should multiply by n-1 because I can choose one vertex that will be not in the red component, then divide by n-1 factorial, and this will be g of n-1. Okay, I think it's correct now. Okay. I'm pretty sure this will be fast. Six seconds. How is it 62 in F1? Interesting. This should be doable. Wait. Let's say that we will have unsigned long 2, which is well, just not square, whatever. So what the issue is? The issue is that it is slow to take something modular, and we are taking modular mod here on every iteration. That's like the only quadratic place. So instead what we can do is we will calculate the sum and take it modulo mod square, but we will do it with if. And now we will say that gi is just x, it will take it modulo, and it will be still correct, but hopefully like 5 times faster. Interesting limitations. Yeah. Not get accepted with n squared on 50,000. It's like it should be heavy n squared. This is not heavy n squared. Like one place, and I can remove taken modulo there. Yep. Then I can get accepted easily. But yeah, there is n log squared solution with online 50 and stuff. I think there was a blog about it recently, so if you're interested you can try to find it. Thanks for watching. Well, problem D was education. Problem F was educational on how to squeeze n square, because like that's useful, right? Thanks for watching, bye.